Humans have always strived to try and see the unseeable, be it the supernatural, microscopic science, or deep into outer space. There's that drive to try and one-up the human eye. As a computer scientist, this concept intrigues me. As a plant lover, it challenges me. I find nothing more frustrating than realizing too late that my plant is diseased or under stress, be it too much water, too little sunlight. By the time the visible symptoms appear, ones that my eyes can see, whatever it is has already taken a good hold of my plant. Imagine being able to see the future though, to see the disease coming before it shows. That was my challenge, and to do it in such a way that is cheap, easy to use, and accurate. First things first, I want to better the human eye, which means I can't use the human eye, so I turned to cameras. In my research, I found that a plant under stress undergoes internal changes that alters the reflectance of the plant's leaves. The wavelengths most sensitive to these changes can be found in the near-infrared range. Aha, infrared cameras. They're fairly affordable. But have you ever looked at an infrared image? If you put two images side by side, one of a healthy leaf and one of the same leaf under stress, you're not going to see much of a difference. Infrared alone doesn't seem to fall under my easy to use category. The differences in infrared reflectance are still too small for me to see with my own eye. This is where machine learning comes into play, more particularly deep learning. I put together a system designed specifically to learn these small differences in infrared reflectance. Now, while the system has the ability to learn these differences, it still needs examples to actually learn from. So I collected my own dataset. I got over 1,000 images from 6 different plant types. I chose dehydration as my plant stress factor. It was easy to implement, not watering a plant doesn't take too much know-how, as well as easy to measure. You just use a moisture content meter. While investigation is still underway, I have some preliminary findings that I can report on. These were conducted on spinach leaves only. I noted that when classifying advanced dehydration with visible symptoms, my infrared image system outperformed the visible image system by 15%, with an overall accuracy of 95%. However, the focus of this research is on the stage where symptoms aren't yet visible, the early dehydration stage. In the early dehydration tests, the visible image system struggled, obtaining a 25% accuracy. Excitingly, the infrared image system outperformed it significantly by obtaining an accuracy of 70%. This accuracy could also be increased by using larger data sets. While there's still a lot more testing that needs to be done, these findings show that my idea is definitely a viable one and has the computer science and plant sides of my brain very excited.